Okay, yeah, welcome to another episode of the AutoML seminar. So today we have the great pleasure to have Nick Erickson which is a senior applied scientist at Amazon, so AWS in Seattle, right, Nick? And today, he's going to speak about AutoGluon 1.0 and tell us how they get SOTA and with Zeroshot-HPO and dynamic stacking. So, and Nick, the floor is all yours.
Awesome. Thanks so much for having me. So excited to finally give a talk at the AutoML seminar. I think because of the time zone difference, I didn't get around to it earlier, but happy to be doing it now, and especially talking about AutoGluon 1.0, which has been in the works for a very long time now. So let's get started. As mentioned, I'm Nick Erickson, and I work at AWS. So first, very fast recap in terms of what we're talking about when we're talking about AutoML, or at least what AutoGluon is talking about when we're talking about AutoML, is that you bring your data, could be images, text, tabular, any form really, but we're talking about supervised classification or regression. And then you basically pass that data into something, for example, AutoGluon, that basically trains a model, and then that's then able to make predictions on new data. And so this is the scenario that we're really talking about. And we want to build a system that is able to do this as generically and powerfully as possible. So in terms of building an AutoML system, I think there are 7 steps needed for an AutoML revolution. And when I say an AutoML revolution, what I mean is basically for AutoML to become the dominant form of people using ML in practice. So for example, XGBoost currently is the dominant force of most industry usage of machine learning, at least on like the tabular side of things. If you go to most industry places and you look at the code repos, you'll see XGBoost literally everywhere. And it's kind of a word of mouth thing at this point. That's like passing on the torch of like, this team used XGBoost, so we're going to use XGBoost. We're going to copy what they did, basically, right? And there's tons of information online about XGBoost. Like if you Google any question you want about XGBoost, you'll find the answer. And it's a good system, right? It works. It's quite accurate. It's relatively easy to use, but AutoML can push that ease of use way up and the accuracy way up. And I think that if we do these 7 things, we can finally replace XGBoost from the throne of tabular methods, and then also, in other areas too, for other stuff. So 1, it needs to be easy to use and widely available. Just pip install and works on basically any type of hardware that you would realistically be doing machine learning on, and being able to deploy it on any hardware you'd realistically want to be using it on. It needs to have strong performance. So what does strong performance mean? It's kind of a bit nebulous, but basically compared to things that aren't AutoML, it needs to be as good or better, ideally better. Basically, AutoML shouldn't be a toy thing that you kind of use initially, and then when you get serious, you use the serious models like XGBoost and whatever, right? AutoML should be like the golden standard of performance. It needs to have fast inference speed. Basically, it has to be something that you don't throw it away when the constraints of your problem get tight, where it's like, oh, well, we need sub 50 millisecond end-to-end latency. So that AutoML is out of the question because AutoML is too slow, right? We can't have that. We need to be able to satisfy those scenarios that are common in practice. It needs to be stable and reliable. It can't just crash on you because the data is a bit too big, or your machine has more CPUs than we thought it would, so we spin up too many processes all at once and get an out-of-memory error, or there's missing values, right? It needs to be built like a tank and just roll over basically any data set and get you a result. It needs to be customizable. Basically, there are a lot of times in industry where people already have solutions that work quite well. And we shouldn't just force people to throw those solutions away. Rather, we should give them the tools necessary to integrate those into the system. So for example, custom model support, custom metric support, the ability to tweak which models they train in what order, things like that. For example, if they know, oh, neural networks are not good on this problem, they take way too long to train, then you should give them the ability to say no neural networks, or this, or maybe they have an XGBoost model with these certain hyperparameters they really like and does really well. Well, you can have them specify those exact hyperparameters into the AutoML system and train it to replicate that into the AutoML environment. Those things are very important to earn trust with users. It needs to be insightful. I used to say it needs to be, what's the term? I forget the term. There's another term for this, but I changed it to insightful because I prefer this. Basically, it needs to provide the user with a feeling that they better understand what is going on inside, and also basically understand some aspects of their problem. So for example, what's the feature importance? What are the Shapley values, things like that. Maybe what are the data types, special data types of their data? Is there time series features, things like that. But being able to provide that information that earns trust with the user and also helps them in doing their own improvements later on, especially with like feature importance and things like that. They can then deep dive into their data and try to improve it. And finally, deployable. Basically, once you've done all these things, great. Maybe you've trained on your laptop or whatever, but at the end of the day, you need to actually be able to use it in production. So for example, edge devices, or cloud endpoints, things like that. You need to take what you're able to do locally and transfer that to production. And I think once you do all 7 of these steps, you're in a pretty good spot. So let's move forward. So one of my coworkers created this slide and I really loved it, so I put it in here. I think that AutoML is very similar, if you remember the Mac versus PC ads a long while ago, to this situation, right? It's basically AutoML is everything's ready to go, and then XGBoost, for example, is, oh well, you need to then do your data pre-processing, right? Your categoricals, you need to one-hot encode them, or you need to now pick your HPO method and tune it, right? It's more steps, more areas where people could go the wrong direction, right? More room for user error. So we try to simplify things, basically. So AutoGluon overview. AutoGluon is an AutoML toolkit that democratizes machine learning. It automatically builds accurate models for image, text, time series, and tabular data with just 3 lines of code. And it's open source and easy to install. Just pip install AutoGluon. And you can find us at AutoGluon, auto.gluon.ai. We're also on GitHub. So we're open to contributors, and we have a very active community. So AutoGluon is adopted by Amazon's Machine Learning University as the primary toolkit used to teach over 24,000 Amazon software development engineers machine learning in 2022 and 2023. It's also deployed in over 600 Amazon projects internally and used as the backend for multiple AWS services such as SageMaker Autopilot and Canvas. It's also used by over 150 companies such as NVIDIA, Intel, Capcom, Mitsubishi, Oracle, etc. Also, the NBA recently is using AutoGluon for their next-gen stats. So if you ever watch a NBA game and they have like the Amazon stats tracker thing pop up, AutoGluon's there. So that's pretty cool. And it was also the opening keynote of the AutoML Conference 2022, which is a great honor. Okay, so AutoGluon AutoML. So prior work, again, this is not fully comprehensive, but I think that a lot of systems kind of fell into this area, is that a lot of AutoML was model plus hyperparameter selection back in, say, like 2019 or so. And basically, AutoGluon is very different in the sense that it relies on strategies that win prediction contests on sites like Kaggle, instead of going down the hyperparameter optimization route through thoughtful data preprocessing, model ensembling by multi-layer stacking, a greater emphasis on modern deep learning techniques, and boatloads of tricks and optimizations, basically. So for this talk, because we just have 40 minutes, I'm only going to cover tabular. But we also have multimodal as well as time series that both are able to achieve quite strong results. But for this talk, I'll just be covering tabular and the stuff we're working on there. So you may be familiar with a competition called the Netflix Prize. It's an infamous competition for $1 million prize pool a long while ago that basically beat Netflix's recommendation algorithm by 10%. And then you get the $1 million. And so this took years for anyone to be able to do. And the final solution was hundreds of machine learning models all ensembled together in a complex method called blend stacking that was practically invented for this competition. Basically, the final solution was so complicated that Netflix didn't even use it. And so I would call this a monster in the sense that it was the most powerful thing anyone could come up with, but it was also so unwieldy that had to be impractical. And if you go head over to Kaggle, back at that time period, that was also the dominant strategy, is basically what's called this multi-layer stack ensembling technique. It was kind of like this black magic going on that people who were very, very familiar with machine learning competitions would do to eke out the peak performance to win out on Kaggle competitions. But always it was seen as like very impractical for production scenarios. It would take too long to train, the inference was too long, it's way too complicated to implement all that stuff. But my question is, can we tame the monsters? So can we make them reliably performant and stable for various data sets, assemble them without need for expert knowledge from the user, train them in a reasonable amount of time on a wide variety of hardware, enable flexibility to satisfy user constraints, and most importantly, hide the complexity behind an elegant API. AutoGluon strives to achieve these goals. AutoGluon strives to tame the monsters. So how do we go about this? So what's under the hood here? So first off is model variety. So basically, we want to maximize the diversity of models that we're training because at the end of the day, we're going to ensemble them all. And basically, diversity leads to strong results in ensembling. So we take the best of open source. So XGBoost, LightGBM, CatBoost, the classics for boosting methods. We take scikit-learn for random forests, extra trees, k-nearest neighbors, etc. FastAI, they have a nice pre-built tabular neural network model that we adapted. PyTorch, we also create our own custom neural network models. And then also Hugging Face and Tim for both text and vision models. And then basically we take all those models, and when we train them, we implement our magic ingredient, which is multi-layer stack ensembling. And so the concept is, given input data here, predict basically train a set of models as normal to an extent. And then basically you predict on that data to get prediction probabilities, and then you concatenate that with the initial data to basically generate automated feature engineering effectively, where the feature is the prediction probability of the model that you trained. And then you feed that extended data set into the next layer as the training data. And then you can repeat this process if you want as many times, and then finally do a weighted ensemble that generates the final output. Now, normally, if you did this naively as I just described it, you would overfit terribly and the result would be awful. So we need to do some safeguards here to avoid overfitting, which is basically doing cross-validation on all of the models and then taking the out of fold, is what it's called, prediction probabilities of every model and using that at training time as the features in order to basically ensure conditional independence and yeah, basically avoid overfitting really hard. That doesn't necessarily solve the problem. We'll get to that, but yeah, that's the general idea. Is basically you do cross validation for every model, and then take the prediction probabilities on the validation data for every model, concatenate together. This is the data that you then use as the additional feature at training time, and then at test time you just average the test predictions together to generate the same feature. Yeah. So that's it basically for the basic rundown of what we did prior to 1.0. It's like a very simple overall system. Again, there are a bunch of tricks and optimizations and stuff hidden in there that I could do a whole talk on at some point that I probably should, but that's like the core overall idea. So to obtain the upcoming results, we did not hyperparameter tune. We used the same hyperparameters for every problem, and we trained using the same 3 lines of code for every problem, which is this. From AutoGluon to tabular, import tabular predictor equals tabular predictor, specify the label column you want to predict with, call .fit, specify the location of your training data or pass in a pandas data frame, set your preset if you want, such as best quality, set your time limit, how long do you want to wait for it, do you want to grab a cup of coffee, lunch break, going home for the day, weekend, right? Just set your time based off of whatever you want, and basically AutoGluon will just keep doing its thing until it's either finished or until the time limit is elapsed, and then it'll return you your result. And then predictions equals predictor.predict passes the test data, and that's it. All right, so in 2020, we released our original paper where we showcased that we were able to achieve state of the art on the AutoML benchmark. At this time, it was just 39 data sets, but then we also included 11 Kaggle data sets. Notably, back then we were also very stable in terms of how often we would crash relative to other systems. I think other systems have a lot of them have gotten a lot more stable now. So I think we're in a pretty good spot in terms of stability for several AutoML systems. But back then it was actually very challenging to like get an AutoML system to like not crash on arbitrary data, especially like when the datasets get big. I'm looking at you, Diana's dataset. Okay, so yeah, so basically the results were quite promising. So then we kept working on the system basically. And so then in 2022, the AutoML Benchmark authors released a paper, and also Peter Gibbers, who's the primary author of AutoML Benchmark, did his PhD thesis on the topic, and basically where they compare all of the most prominent AutoML systems, and they showcase that AutoGluon was statistically significantly outperforming the rest of the AutoML systems on basically an extended benchmark of 104 datasets. So then the question is, okay, well, you know, you can compare against other AutoML systems. That doesn't necessarily prove that AutoML is useful, right? So another question is, are people using AutoML when things are serious? Basically, can AutoML win a live Kaggle competition? And so last year, in a competition with over 700 competitors, the first place solution actually used AutoGluon to get the win. And this is particularly interesting because the Devastator is one of the top Kaggle grandmasters, and he mentioned that he believes that this is the first time that an AutoML system ever got first in a machine learning competition. So I consider this to be a pretty interesting milestone. And I will note that this is not just only AutoGluon, right? This is a person using AutoGluon as their primary tool, right, for modeling, but they also did manual feature engineering. So we aren't there fully yet where you just do 3 lines of code and you win, right? But I think that this is definitely a step in the right direction. Yeah, and you can go here to see that if you'd like. So that covers basically what AutoGluon was prior to 1.0. So now let's get into what have we done in 1.0. So Multi-layer stacking can overfit. This whole conditional independence thing I talked about, it's a lie. So why is it a lie? Well, so we observed that there is actually a performance loss on about a third of binary classification tests on AutoML Benchmark when you use stacking, which is a bit odd, especially when the performance loss is extremely large in some cases, and it happens on very large data sets that you wouldn't think would be very vulnerable to overfitting problems. So how can we fix this? So a simple example of stacking's failure, and because we only have 40 minutes, trust me, you're not going to fully understand what I'm talking about in my example. But basically, if you take the binary classification dataset adult with only the feature age, it's a very simple, basically one integer column leads to a binary classification, right? And if we train a random forest on this with 100-fold cross-validation, the cross-validation is like the golden thing that everyone says, oh, if you're overfitting, just do more cross-validation, right? It'll solve all your problems. It turns out that cross-validation, not only does it not solve the problem, it actually makes it worse. The more you cross-validate, the worse you're overfitting. And yeah, so basically our validation score is 0.9, our test score is 0.68. So our validation score becomes completely unreliable, and it negatively correlates with test score, basically, which is very, very problematic, because normally in AutoGluon, what you do is you look at each stack layer and you see, basically based on the validation score, you pick the layer that you actually use at the end, right? So normally you would expect, oh, maybe if the stacker isn't very good, then the validation score will tell me it's not good. But here it says the stacker is amazing. It's like incredible, 0.91. But at test, it's terrible. And this is like the worst possible thing for an AutoML system, because you don't have a person anywhere in that logic to say, hey, wait, something's weird, right? It'll just do its thing, and that's it. And this is why AutoGluon did not even do stack ensembling in binary. I disabled it because I realized that there was this scenario that was happening. And when it happens, it's bad, like really bad. You're worse than practically any other solution that you could have used when this occurs. So it was a safeguard. I disabled it. Yeah, and we call this problem stacked overfitting. And I also want to give kudos to Lennart for his great internship, where he deep dived and made these slides for this topic and did a bunch of experiments and came up with a really awesome solution. So yeah, so we want to solve all problems as good as possible, but due to stacked overfitting, our validation score is unreliable, and we have a bad test score because we use stacking. And so an impact of the solution is that we can trust AutoGluon's validation score. AutoGluon works as good as possible when using stacking, and it might become better in general without the leak. So we implemented a very straightforward solution that's extremely effective. As a baseline, there's much more that we could potentially do, and I think that we will try to do, but as an initial baseline, this is a pretty good one. So basically, we created something called dynamic stacking, where we split the training data. Basically, we have a holdout set. We create a holdout set, and then we fit AutoGluon on the training set, or we put the original training data into this train and holdout set, and then we train on that smaller subset training data as normal, AutoGluon fully. Then we validate on the holdout set, and we figure out which layer got the optimal result. And basically, then we pick that same layer to use. We then combine the holdout and the train together to create the original training set, and then we train AutoGluon as normal. However, we take the information as to which layer got the optimal result, and we use that information to determine how many layers of stacking we do, basically to avoid the stack information leakage problem if it occurred on the holdout. So basically, we have a vision of if the problem occurred based off the holdout score. And then there is some nuance, basically, of how do you deal with a limited time limit. And we found that we were able to get pretty good results by giving, I think it was 25% of the time to the dynamic stacking part, and then 75% of the time to the normal part. And this does a really good job of mitigating the problem. Basically, whenever the problem occurs, we find out, and then we avoid doing stacking. And then when it doesn't occur, we continue and do stacking as normal. So we'll get into just how big of an improvement that is shortly. But the next thing that we did for 1.0 is hyperparameter optimization, that thing that AutoGluon never did. Well, it strikes back, baby. It's coming back. All right. So surprisingly, AutoGluon achieves strong results without HPO. I believe of every modern AutoML system, AutoGluon is the only one that doesn't do HPO. And by default, AutoGluon just trains 13 models with fixed hyperparameters that I picked like 5 years ago and never changed. So does HPO even help? Yes, but it's often better to spend time on other things such as cross-validation, stacking, etc. So can we do better? So the current status of tabular models and tabular benchmarking, most recent one is like the Tabzilla benchmark from NeurIPS 2023. I think Colin White was one of the authors of that one, where they benchmark a ton of different models, I think including TabPFN. TabPFN isn't in this table here. But basically they show that, you know, as expected, basically like the boosting models are extremely strong. But they kind of like, they do like a different number of hyperparameter tuning per data set. So it's kind of like they hyperparameter tune to their budgets done for the given model, right? And they get the result. And then they just start comparing kind of like the performance of individual models. But we know with AutoML that basically ensembling is where it's at if you actually want the best possible performance. And so this is a useful benchmark, but it doesn't necessarily give insight into what models should we use in an AutoML system to ensemble to get the best result. So myself and David Salinas, we worked for over a year on something called TabRepo, which is basically pre-computer results for tabular ML. So the idea is that we save the validation and test set predictions for 200 random configurations of 6 model families across 200 OpenML datasets and 3 folds of each. So what do I mean by validation test set predictions? So that actually in classification terms, it's prediction probabilities. But basically, this is the artifact needed to then run an ensembling algorithm on it. So basically, to train the ensembling algorithm, you need the validation prediction probabilities of the models. And then that allows you to get the weights of the weighted ensemble. And then you can use those weights to then get your test score with that particular weighted ensemble configuration. And so, yeah, so basically we train, say, a machine learning, an MLP with a specific learning rate and whatever, basically random hyperparameters through a search space. And another key is that we use the same 200 configurations on every data set, and we always train all of them. So basically, it's a dense set of results. So for a given hyperparameter configuration, it has a result on every single data set. So basically, these 1,200 models are trained on every single one of the data sets, and we have results for all of them. And now what we can do is offline ensemble simulation. So basically, we can use these pre-computed results to search for an optimal portfolio. Not that necessarily does say like set completion where it gets the best, you find like one of the models that does well, but rather we can actually directly measure the ensemble performance. And this means that instead of having to, when we're checking to see, does a particular configuration of models lead to good performance when we ensemble them, actually having to train them all, rather we can just simulate it because we've already trained all of them with TabRepo, and we can just load the prediction probabilities directly and then fit the ensemble in seconds. And then this allows us to then iterate like thousands of times faster, basically, or even like millions of times faster, really. And so long story short, we're able to find a portfolio that doesn't use stack ensembling at all, that is able in a similar amount of training time to outperform AutoGluon with its stacking enabled. So basically, like the whole thing that like AutoGluon gets its performance through multi-layer stacking, all along, someone could have just like said no to stacking and actually outperformed AutoGluon by just having a fixed portfolio with no live HPO, but rather just doing HPO offline, and then online they just have a fixed portfolio that they use for every single data set. It's the same thing, no stack ensembling whatsoever, and it beats AutoGluon. And it's also faster inference time. So that's great, right? Cool. So we found a better portfolio, but wait, we could do stacking. What happens if we do stack ensembling with this portfolio? And what happens if we do dynamic stacking to fix the leak problem as well? What result do we get if AutoGluon was already the current state of the art prior to those things? Well, we get 1.0 AutoGluon. So I am going out to claim that I think that this is the single largest leap forward in the state of the art in tabular methods in over 4 years. People can maybe argue with me. I don't know if anyone wants to, but I feel like it's probably true. So this has a 75% win rate versus AutoGluon 0.8 with a 7.4% relative loss improvement. If we look at this is the results of the AutoML Benchmark. It has an 82% win rate versus the second best method, so MLJAR, and has a 10.8% relative loss improvement versus H2O AutoML. It has a 63% win rate versus the Oracle combination of prior systems, aka best in hindsight combination, which means that basically it is champion on 63% of the data sets. It also has a 100% win rate versus XGBoost and a 99% win rate versus LightGBM, which for people who might say that XGBoost is all you need, I would argue maybe take a look at this. So now the 2023 AutoML Benchmark results came out actually like 2 weeks, I think, before AutoGluon 1.0 released. Basically where they showed that AutoGluon was able to get very strong results. So this is from the updated version of the AutoML Benchmark paper. So then we went and took this output result file of all the AutoML Benchmark 2023 results, and then we added in AutoGluon 1.0. And we went from an average rank of 3 to an average rank of 2, which if you're not very familiar with how rankings work, it might be hard to understand just how significant that is, but I'll say that it's a pretty big jump. And then another thing is for inference time. So for a long while, basically the concern with AutoGluon was like the inference time. And I will say when we originally released it, it was definitely really, really slow, like really, really slow. But we've done tons of optimization since then, and we've incorporated techniques such as infer limit, which I don't have time to go into too much, but basically it's a way for us to alter our training to satisfy a particular inference speed. And so if we look at the Pareto frontier without AutoGluon, we can see H2O AutoML gets a pretty good trade-off of performance, which is the y-axis accuracy basically, with prediction speed. Going left is better. But with AutoGluon 1.0, and by just specifying the infer limit to different values, we're actually able to establish all the points along the Pareto frontier. So basically, AutoGluon is able to achieve superior accuracy while also simultaneously having faster inference speed at any point along the performance inference speed curve. And to give a perspective of just how much better this is than previous AutoGluon, this is what AutoGluon 0.8 was. So yeah, definitely shifted up quite a lot. Also, thanks to, again, a large part Leonard for his very clever idea to do subfitting logic. And also we did some improvements to our memory our memory checks. Basically, we now have 0 failures on the AutoML Benchmark. I also created some new plots recently. So if we look at rescaled accuracy, so scaling performance from 1 to 0 based on the best and worst performing method for every data set and then averaging or taking that. This is a box plot of that information. So we have AutoGluon 0.8 and then 1.0. And the big thing with 1.0 and the reason why it's like almost always like at the very top here, I think personally is because of dynamic stacking. Basically, it removes a lot of the cases where we were getting very bad performance because of the overfitting. And so it just very consistently is able to find a good solution. If we look at champion loss delta, this is basically if you take whatever got the best result on a given data set, and then you look at what percentage less loss did that champion have than the system, that's what this is. And so again, AutoGluon 1.0 is consistently able to get very, very close to the champion or be the champion. So basically, whenever it's not the champion, it's not far off. It's like has a competitive score. So then there's a new metric that I really like that I kind of looked into very recently, and I shared with Leonard. Is basically ELO ratings. So Chatbot Arena is something that has gotten very popular lately as a way to measure the performance of different LLMs. Basically, you have a person that has types a question, and then two LLMs will give an answer, and then the person rates which one gave the better answer, right? And then they use this akin to kind of so like ELO is used in chess, for example, to calculate players' skills. And so basically it's based off of the concept of like a match where there's two people and then the outcome, and then basically you can calculate an ELO based off of the history of all matches of all players. And so this is how they do that here, and they show that okay, GPT-4 is currently the state of the art. Bard isn't too far behind it. And then there's a bunch of like open source models on the lower end, right? But you can see like the ELOs are relatively, like they aren't that far off. So like 1250 to like 1070 here. The idea with ELO is basically 400-point difference means that there's a 90% win rate for the system that's 400 points, 400 ELO points higher is basically how it's scaled here. And so I really liked this, and I hunted down and found their code of how they did it. Basically, it's in a Colab notebook somewhere, and I copy pasted that and then like made a couple edits to make it work. And with the AutoML benchmark, what we can do is we can, for every data set, well, we can just generate pairs of results. So we say this framework versus this framework, which one got the better performance? Okay, that one won that battle or that match, right? And you just do this for all possible pairings on the AutoML benchmark, and you can create an ELO. And so this is what we get. And so I have I basically standardized to have random forest at exactly 800 ELO for reference. And we can see basically cat boost here. So I also incorporated like XG boost, LightGUM, and cat boost based off of AutoGluon's default run, as well as like the tooth random forest. Note cat boost is very, very strong for a single model. And then we have the AutoML systems, Gamma, AutoScikit-Learn, MLJAR, FLAML, H2O, Light AutoML, all having relatively similar ELOs. Then we have AutoGluon 0.8, which is a pretty nice jump up, about 130 ELO. But then we have AutoGluon 1.0, which is at 1,480. So basically, the gap between AutoGluon 1.0 and AutoGluon 0.8 is larger than the gap between AutoGluon 0.8 and Light AutoML. So basically, we've like over doubled like the ELO gap effectively in 1.0. Yeah, so I quite like this metric. I think that us as a community, we might want to take a look at this metric because I think that it provides a lot of very interesting information in a pretty digestible format. And it's also very robust to adding new methods in. It doesn't like change dramatically if you added like methods that are poor into the plot, but yeah. And then another thing that's interesting is if you look at changing the budget. So for example, with AutoGluon, if we changed it to 1 hour time limit, 30-minute time limit, 10-minute time limit, 5-minute time limit, this is the ELOs of all those different variants. And so actually with 5 minutes training time, AutoGluon has comparable ELO to other AutoML systems with 4 hours. So that's an 80 times training time reduction basically that you can get to achieve the same performance as before with other systems. which I think is pretty interesting. And so what about, again, in practice? So, AutoML Benchmark is interesting, but, maybe you can be overfit on it or things like that, right? So basically, I think the real test is, do people use it? And so right after we released, basically the first KO competition that occurred was Playground Season 4, Episode 1. This is during the competition. Basically, these are the public notebooks. I sorted by public score, so basically the best public notebooks. And then I looked through each notebook to see what they're doing. And all of the top notebooks, basically, I think the first 11 all used AutoGluon in this competition, which is very interesting. And then additionally, the final, at the end of the competition, basically AutoGluon, a solution that used AutoGluon took second place out of 3,777 competitors. And this was a month-long competition, so it's not like it was something super quick, like it kind of endured. And then, so then the next competition started February. And as that competition started, basically someone made a post that said that they decided to use this baseline solution produced by AutoGluon, which got them to first place on the leaderboard during the first couple of days of the competition. And also the second place solution was also AutoGluon at that time. And then third was Flamel. So basically AutoML all the way. And then if we look at today, there's currently 2,044 people that have entered the competition. It's halfway through the competition. If we sort by best, we can see that the top 2 highest scoring notebooks use AutoGluon, and it ranks 6th out of 2,044 currently on the public leaderboard. So yeah, I guess as a recap, AutoGluon 1.0, it looks like the performance is pretty good. It's 3 lines of code, runs on raw data, no need for processing, 101% versus XGBoost, available pip install AutoGluon. Yeah, and then there's all this stuff that I'm not going to have time to do, but basically, suffice to say, you could run it on the cloud, 3 lines of code, deploy on the cloud, yeah, predict on the cloud, 1 line of code, 7 steps to an honorable evolution. Basically, we did a lot of cool stuff. Oh, oops, I'll go back. Basically, I think that we achieved all the 7 steps of the AutoML revolution. I think that now is the time that people should use AutoML as their go-to tool, effectively. In summarization, I don't have time to go through all these points, but yeah. And then I think that there is an 8th step, which is very important, which is ease of contribution. Basically, how do we make sure that this continues forward and can scale to the community's needs without basically just the team that's working on it going insane? And I think this is a very interesting problem, and we're building tools like AutoGluon Bench as well as Tab Repo to facilitate that. Tab Repo, basically the idea being that anyone has a new model or a new idea, they can run it through Tab Repo, where basically they cache the prediction probabilities on every data set. And then we can run the simulator to see if the simulator would pick that model or method as part of the portfolio that we would select to do ensembling with, right? So instead of having to rerun all the methods that we already ran, it's just them having to run their new method. And then we can run the simulator to see if it picks it up. And with Bench, basically the idea is running the full benchmark just on PRs directly. So just like someone submits a PR to AutoGluon, we run the benchmark on that PR by just typing a command, and a GitHub bot then goes and launches a cluster of machines to go do its thing and then does a bunch of analytics. So cool. And then, yeah, we're working on things like AutoGluon Dashboard, which is like a website that's spun up that highlights all the results and is sortable and all this stuff. And then AutoGluon Assistant, basically, yeah, currently AutoML in 3 lines of code. And then, yeah, can we go to AutoML in 0 lines of code? Can we create the world's first AI KO grandmaster? I think that that's going to be interesting. So yeah. Bench Assistant coming soon. We have a cheat sheet, tells you everything you need to know. Just go to our website. And of course, I have to also thank everyone who's worked on the project. This is not the full list, but there are many people who have contributed to the AutoGluon project, and especially like these are the people within the Amazon AutoGluon team. yeah, it's been a wild ride so far, these like past 5 years working on this. And I hope that only better things lie ahead, basically, for the field of AutoML. So yeah, thanks everybody. And I think we can start the Q&A.